you, folks. Yeah, all right. Thank you very much. Even as I was giving the introduction for today's study, so the focus for the whole of this uh, short course is to equip you so that wherever you go to, in regards to the individual research whether you're doing, you'll be able to catch up and then see how we can all support in continuing with that work. So yesterday we had a build up session on what we had in the first day. And the story was simple. The story was that before you consider epidemiological modeling, you need to first identify what are you really aiming at? Are you planning to do? That's the first that you need to identify. So having been very specific about what you want to do, then we think about, okay, which structure, in other words, which framework or which model can help me meet this objective. Then you explore about, okay, which module structure or module type will help me in best answering this question. Then following that, you think about what are the assumptions that I can make in order to arrive at my research objective. So which assumptions should I make? What should I bring in? What should I take out? Why should I say maybe this one is based on expert opinions? Which ones? What do I know from data? And that comes to the next step. That is to consider your parameters that you need for building your model. So then you think about, okay, what do we know from literature? What do you know from data? Which information can we get from experts? So based on that, you're able to get the parameters that you need for building up your model. And then when that is done, you after putting all your input into your framework or your model, you get some output. And then we also understood that when you get the output, that is not the end. You need to analyze, you need to check the output, whether that makes sense. Does that conform to what you expected? Or are you getting something different? If in case you are getting something different from what we were expecting, what are the key contributing factors? If in case it deviates from what we know already, what is causing the deviation? Is it because there is something missing in your model? There's something that you didn't consider. What is happening? So that gives you the time for you to explore that part. Then so following that, then you can go ahead with your sensitivity checks. So you check, okay, if I change this parameter, what happens? If I increase this parameter value, what happens? If I decrease transmission, what happens? To check that everything is working well. And then following that, you can take it up, whether you're doing a scenario analysis or whatever, then you can try to come with an output to inform policy decisions. Today's section is not different from what we did yesterday. So yesterday we talked more about the theory part, but the issue is what about the practicality? So today's focus is going to be on really trying to, okay, if I have a model, how do I even to go to the stage where how do I put this into, let me quote my machine, the machine that I'm building. How do I try to test that? How do I try to run my machine? How do I try to start my machine, the engine of my machine, so that I get the output that I'm looking for? That is what we are going to look at today. So it's in 2 sessions. We are going to go through everything theoretically. Then after this, you switch to R. So we are going to share the R interface so that we all see how we take it from one step to another. And the whole aim is, at the end of the day, this aims to equip you or to support you, especially when it comes to you trying to code your model. That is the overarching aim for this session. So even as we did yesterday, let's interact wherever we need to, and always draw my attention if there is something that you are missing. Let's go together. Yeah. So I've already explained the purpose or the core objective for this session, and the first one is what we did yesterday. So It's just a recap from yesterday's part. And then today we are going to focus more on the epidemiological computation. That's what we are going to do more today. Another story. So the same, even as we had an idea about if I want to prepare Machuke, what are the elements that I need in preparing that? We can also see the same analogy as me trying to maybe go for a journey that takes me from Nairobi to Kampala. So if I am moving from Nairobi to Kampala, what are the key things that I will need for this journey? We can also see modeling as in such way, or what we're going to do today in such way. So now we've got some tips, we've got some techniques, so we are here. And if you're making any journey, so you think about the transport, the steps, or which transport are you going to use? Are you going to get to your destination via train or bus, or are you going to walk? You need to consider all these factors. And the more you are able to prepare here, so this is the step that mostly lots of people. So if you will be very happy here at your destination, if everything go on smoothly for you to reach your destination, much of the work has to go here on the preparation this phase. So if you are able to build this place well, then if you want to achieve here, or we want to get here, it wouldn't be any big problem because this foundation is strong, and that is what we are the whole story that we are saying for all these few days that we've been chatting together. So this I saw this figure, and I think it's very informative. It captures the whole background of epidemiological modeling, including the different stages and different steps. So yesterday, if you remember, we talked about biological question, and then that is the first where you start from. And then based on that, you think about a model structure that will help me do this. Then under that, there might be some data that you might have to inform you to know whether your model is performing better or whatever. So this data is going to help you to know, try to compare and validate your model, to see that does it really give me something which compares well with data. And most of these data we can find from laboratory parts, so people will be doing experiment on that, and clinicians will be giving us a number of cases about any disease that might be our interest. So following that, then we need to do some mathematical analysis, make sure that the model makes sense mathematically. Are we saying at the end of the day, are we getting output which involves maybe negative individuals? It doesn't make sense mathematically. So we need to take into consideration all these elements. And if there is a need for us to do parameter estimation, even as we mentioned yesterday, then we go along that route, and then you get an outcome. But that's not the final phase. We get an outcome, we do sensitivity analysis, we do a sanity check, and that's what we are going to do. So this thing catches the whole idea about what we are going to do together today. So following yesterday's session, then we had the last question, but we said that let's wait and we continue with that question today. So someone questioned that if I am choosing a model to answer my research question, what's the right way for me to do this? How do I go around this, since we have lots of models on market? So how should I go around this? So based on the preamble that I just gave, always we first start from identifying what you want to do. So identifying what you do, and even taking us a little bit back to the analogy that I was having in regards to if I want to move from Nairobi to Kampala. So the first thing is you need to first identify where are you now, and where do you want to go? So where you want to go is the research question. We've identified that, oh, the objective of the work is at the end of the day, all that I'm looking for is to be in Kampala. That is all, that's my aim. Then this is where you come and think about your model. So how do you now get to Kampala? The fact that people are using flight doesn't mean that by all means you have to also go and use flight. No. The fact that someone is using a car doesn't mean you have to also go and use a car. Maybe you cannot afford that, but maybe you can afford something cheaper. You can maybe go by a public transport. That one may be cheaper and convenient, and you might have all that it takes to take that route. At the end of the day, you will get to Kampala. That's what your aim is. So sometimes if you don't maybe take care, you might be sometimes you might be like discouraged, or like you might be scared about some complicated models that people are putting up and whatever. And even as we understood yesterday, whether it being complicated or simple, the question is that the appropriate or the suitable framework that can help me to get my research objective? Is that the right tool to be used? Those are the things that you need to consider. So it's not about we have this one way form of design the model. So it all depends on what are you looking for, and that will inform you to know what will appropriately suit your research aim and objective. I hope that is helpful. Brenda, I think, yeah. So today, let's consider a very simple model. So we consider our SIR model, where S is those who are susceptible, I is those who are infected, and then R is those who are removed or recovered in this. So let's assume that for the purpose of this session, R is recovered individuals, and in between any two compartments, there are some movement that is going on. So we can see that people can move from where the arrows show indicate where the corresponding movement. So as people in the S class at any particular time T can move into the infected class at any particular time, and then those in the infected class can also move into the recovered class at any particular time T. Now we don't see reverse arrows. So what this indicates is there is no way in this model we expect that people in the infected will move to the susceptible. There is no arrow indicating that. So we will not think about that. That is not part of what you're doing now. And likewise, you don't see any movement from R back to either I or S. There is no movement like that. So then we see it as it is. And how we see it, that's how we are going to write an equation for. So let's maybe try to explain some of these terms. So we are just saying
Mark,
that...
Mark, just a minute. Can you hear me, Mark?
Yes.
I just want to know who Jacqueline is. Jackie, who are you? Jackie? Mark, can you stop sharing? Did you hear?
Jackie. Yeah, Jackie, how are you?
Yes. I'm well, thank you. How are you?
I'm also doing well.
Yes.
Are you in Demus Fellows? Sorry.
Which meeting is she targeting?
Sorry?
Which meeting is she targeting?
That evening, it's a preparation.
No, it's another meeting. It's another meeting. Let me help her. Mark, you continue. Okay. So, Jackie, I'm sending you a message on the WhatsApp. Please send me a message and I give you the chevening link.
Okay, thank you.
All right, thank you. So shall we continue? So we are saying that people in the S class, they are susceptible. So that means when there's any effective contact between someone that's susceptible and then someone in the infected class, there can be transmission. And it's not all these contacts will see to infection. So then we see there's that probability that if someone who is infected comes into contact with someone who is susceptible, then there's a certain particular, there's a likelihood. It's not everyone that gets automatically become infected after that contact. So there should be an effective contact. So then we quantify this parameter to represent that. And then we're saying that, okay, those in the eye can also recover at rate gamma. So these rates are very useful, and that they define our parameters, even as we understood yesterday. And then we say that N is our total population. Therefore, at every particular time in the population, we assume that the whole population, if you want to know the number of individuals in the population, that would be individuals in the susceptible plus those who are infected plus those who are recovered. That form the total number of individuals in the population. That is very useful when we get to sanity check. So we will get there soon. Now, I want to what I explained with the diagram. That's a model diagram. That's the model we are using. That's the framework we are using. So how do I represent this in mathematical form? So all that I see, or what this is representing, is that. So we are going to say that the change in those who are susceptible with respect to time is based on this. So what do I mean? Those in the susceptible, at any particular time, you saw that there was only one way that people can move from that compartment, and it is through this this term. So where there is an effective contact between a susceptible and an infected, and then that is also defined by the transmission probability that affects people, or that determine number of people moving from the S to the respective counterpart. But when we check the I, we saw that people were coming into the I. So look at something in the S. Here we are having negative. This is representing that people are moving out. It is very important to bring this negative. That means the S is always losing people. That's what it signifies. But here, we didn't put any negative here, but we put positive, meaning that those people who live here, at the end of the day, they are coming into the I. They are joining. So it becomes addition. That is why we have plus here. And if you check those who are leaving the I due to recovery, that one, because they are leaving, we are having negative sign there. So it is important. The signs are not just there. They are very important in telling us which terms are coming in and which terms are going out. And then in the R, if we can recall, we saw that the R always receives. So people just recover into the R class without losing anybody. Now, in getting this in a very simple way, so we want to discretize it. So discretize this means, instead of we looking at every microsecond, every minute, every second, every microsecond, every small point in time, we don't want to do that, because that is becoming something very complicated, and it might not be of any public health importance. So if, for example, we are talking about not knowing number of people who are infected with COVID. So if you said, okay, at every particular point in time, maybe, so when it is 1 a.m., there were 20 people. When it is 1:1, and don't forget, between 1 a.m. and 1:1, there is time there. So then you need to check, but it might not be of a use. And also, maybe the data available for us to do a comparison are usually not in that form. They don't give to that small time unit. Mostly we get them per day. So then, for simplicity's sake, let's assume that, okay, you want to study this per day. However, if you are working with the disease, or if it will be very important for you to better understand the dynamics of the disease. If you consider smaller time steps, you need to do so. So, or whether to use a very small time step, or to consider it a daily time step, or to consider monthly time step, or yearly time step, it depends on what you're doing. But as a general rule, the smaller the time steps, the better you're able to realize the dynamics of what is happening. So the equation that I showed previously, that I've just rewritten that here, they are the same. This is in a discrete form. So what I'm saying here is, if I want to know what is going to happen, so in that one, we saw that one, if I'm talking about what is going to happen in the next time step. So for example, let's assume that we are in the initial time step, so t is 0, let's assume. So if t is 0, so then that means that t plus 1 means that is tomorrow. T plus 2 will be tomorrow on Friday. So if I want to know what is going to happen tomorrow, then it will, what I should know, or what will happen tomorrow is equal to what is today, what is happening today, minus, and then the term that can cause that movement of people, whether in or out. So what is happening tomorrow is based on what happened today. That is what we are saying. If you check, so that is for the S. So the susceptible of what is happening tomorrow depends on what happened today, which is true. And if the same thing for the I, and then the same thing for the R, that is what this means. And the advantage of this is also to help us when we get to the coding part. It is the same, we are going to use the same analogy. That is why I also wrote the equation in this way. So the one thing that I think that will be one of the advantages of this, maybe participating in these courses. There is this, there are so many packages. So we have a very common one is LSODA in R for epidemiological modeling. There are others that we can also think about. But there is this particular package that is quite new. It's not very old. And it is very useful, especially when it comes to epidemiological modeling. So what it normally does is it has a user-defined interface that it allows you to put in all your model parameters on all your inputs. So when you are done with that, then the code is being designed in such a way that it will transpile everything into C++. Now, if you compare the speed of C++ to R, C++ is very fast in that sense. So it's automatically you don't do that. So you have to, all that you have to do is just, you're going to work in our interface. Okay, you're going to put all your module parameters and everything there. Then how the code is set is it will do that transpiration. So it will transpile everything to the C++, and then you get the output. So you get a form of something which has been broken down for you in R. So this is where you're going to now run your simulations and then look at your output. And I find it very handy, because if you compare the speed of this to the normal LSODA that we know in R and other packages, this one surpasses them all. And sometimes you can have a very complicated model because of what you want to do. You need to put in more compartments. You need to put in more parameters. And the more you put in more compartments and more parameters, the more you have to experience, or you realize the computational complexity of the model. So having packages like this is very handy in trying to do that. So now, how do we try to take everything into that this package? So here, everything here is we are going to do the same thing in the R, but I'm just trying to explain how it works. What we do is, even as I explained the equations that we've already had. So the same thing, we are saying that for those in the S class, in the susceptible class, we are going to update it. Okay, so we can see this as ST plus 1. So the time step, so that's why I brought this equation here. So we are going to update it. But for the next time step, what is going to happen is the number of individuals who are susceptible will depend on those who are susceptible now, and then those who are getting infected, that is the beta times this parameter. That is what it's going to be based on. So the same thing, I've just rewritten this in this form because I want to use that in R, and in an R I don't want to be using the subscript. That's why I am using like these letters to represent the corresponding ones here. And the same way, if I want to also write the equation for those in the I, so this is a sign symbol in R. So I would say that, okay, those in I, for the next time step, is going to be based on those who are in the previous time step, and then plus the movement. So those who are coming in from the susceptible compartment, those who are getting infected, minus those who are going to recover from I, that is a gamma. And then if I want to talk about those in the R, so then I say, okay, I'm going to update it. And that update is based on those who are already in, plus those who will be coming into the R from the R. So here, these individuals. And then I'll say, oh, my total population is when I sum my susceptible to the infected to the recovered, because we assume that the whole population is partitioned into 3. Okay, so if you are not, and there is mutual.
Akamere ngompadde kadagala. Chichi. Did I tell you I'm sick?
Okay, let's continue. So there is that. George, can you please
George, kindly mute your mic. George, kindly mute your mic.
Okay, thank you very much. Yes. So these are the main equations that we are trying to write in Odin. So we're going to write the same thing in into this form. So what's next? So even as we discussed that the steps. So we've in the model we've already inputted the main equations. So what is the different movement? What is the what is representing the different transitions in the model? So we've been able to put that down in the code. So the next thing is, then we think about initial conditions. Initial conditions are very useful. At least we are telling the model that okay, at the start, this is what I know to be those in the susceptible class, those in the infected class, those in the R class. So all these are just variables. So I could have written X, Y, or Z, but because I want us to get it, I want to make things as simple as possible. So that when you see S initial, this is S initial, but that's a short form, S initial condition. And then this is I initial condition. So I'm just telling the computer that, okay, you know what, anywhere, if you're to request for my initial condition, put this there, so that it doesn't become something. I don't want it to become something fixed, because I can so that I can always change it at any point in time. So just put something variable there, and then wait for me. I will supply you with the actual number or actual number of individuals in that compartment later. So that's what I come here beneath. So then I'm saying that The S in it that I'm talking about here, that's the initial condition for the dose in the S. I'm going to supply a value for that. Now, that is what this means is, so user, and then I put 1,000 in that. If I don't put anything here, what I'm telling the computer is, okay, now wait. I'll supply this number later. If I don't put anything here, that's what I'm trying to say. But if I put something here, for example, this one, I put 1,000 there. What I'm telling is, okay, fine. I can supply you this number later. But if I don't give you anything, use this one as a default. If I don't give you anything, so the same thing applies to all the other parameters and then the initial condition for the state variables. If you see, so when you are writing your code, whenever you see that in the user, there is a value there. What it says is a default value. But when you get to where you are running the code, you can always change this. So when we get to a situation where we are doing sensitivity analysis and when we are trying to check the model validation, sometimes I will say, let us change this and see what happens. So you see that these are the values that will be changing there, but it will be overriding these ones. But
Mark, we can't hear you.
Can you hear me now?
Network. I think it's her network because
Okay,
personally
now
I
we
was
can.
hearing.
Now I can. Thank you.
Okay. Thank you. Yeah, so the key thing I want to communicate here is if you just we have to supply our model with initial conditions, and then if you are whenever you're using the model Odin package, if you see that there is something within the user, maybe you are by the time that you are coding, you are not really sure about the value that you have to set for your initial condition. You can leave it, but just make sure that you bring user and then open bracket then later you can supply it. But maybe if you have maybe a foreknowledge, you can just put something there so that maybe even if you don't put anything there, it will take that default value for you to at least build on to get something better. Then having done that, what happens? So you do this on the Odin, so it has a domain specific platform. So that's as until before this point, all that we're doing, we do it there. Then we will save it. We are going to save that separately, because if you run that one alone in R, it will not work. Don't worry. We are going to do examples on that in R so that you understand me better. But what I'm saying, all that I've already said, all those things are the things where we are going to input on the Odin domain specific platform. Then we save it. Then we open another new tab in R. So that's where we are going to call what the one that we saved, the one where we inputted the initial conditions, the main model equations. We are going to call them now, but we have to ensure that where we save that file has the same like they are all same in the same file. Let me put it that way. For where I want to save this one so that you can call that. So the code is just write Odin.Odin, and then you just link that path. Okay, you link that path where you save that SI model. So the SI model, this is how I for example, I save it. So I'm calling it here. Now when I call, I get a generator. So this generator is now, it now combines everything from the equations, from the initial condition, the parameters, they will all be here. They will all be in the generator. So then, if you remember, I just told you that you can always change the initial conditions that you supplied before. So this is where I'm going to do the main running. So what I'm going to tell the Odin is, okay, I just want you to create something new for me. Okay. I just want can do that here. This is the right time for me to do it. If I don't put anything here, it's going to take the one that I supplied earlier. So then I also do for the I do for the R. So I assume that, okay, R, initially no one is recovered from the disease. And then I say, okay, my beta, my transmission rate is 0.2 per day. And then my gamma, recovery rate is 0.1 per day. So this is where, so all these are going to override what I initially gave. So then that gives me the main model. So now everything is now set because I have my equations, I have my initial conditions, I have my parameters, everything is set. So this is the time that I can then set the time range for me running this. So then I can set the time range. So how long do I want to run this? I want to run this for 100 days. That's what this means. Okay. You can run it for maybe 100 years. So you have to always indicate. So for example, if I want to run it for 100 years, that would be 0:365 times 100. That would be my time period. So then having got that, then I can do my running. So this is just the run, do the code for the running. So the S, then I'll call, there's a run function within that, this S, the one that contains everything. Then I'll just say run my T, where the T is the timing. Then I put that there. So then it will run and give me the output in a data frame. We are going to do that, but I just want to quickly take you through how the rationale behind that. So now after the models, so now we are done with the running. So we have got our output. Then what next? This is where we do our sanity check. So the sanity check, if you remember, I told you that now if you look at the population structure that we have, the model, there is no way people are rather coming in, some are going out. They all remain within the compartment. So that means the population is constant in this case. So that means that if I run for time point 0 to 100 days, at every point in time, my total population has to be the same because no one is coming in and no one is going out. For me to know how things are really working well. But if in case maybe people are rather, I'm losing people, maybe today the total population is 1,001, but tomorrow it is 1,005. So no, there might be something working wrong because with this, when I showed the model, the arrow, there was no way people are coming in from the outside, or there was no way people are moving from my main compartment to the outside environment. So I can check that to see that things are really working well. And then also one thing to also look at is what is the dynamics in each of these compartments, because you saw that in this, the S always leave, those in the S always leave to the I, and those in the I always leave to the R. So that means we have to like assume something that like always the S will be declining. That's something that we should come to mind. Well, there's no way the S, those who are leaving the susceptible, they are getting replenished. Always people are moving out. So that means I should see a graph of something of the S maybe always declining. That should something come up. And so that means if I plot and don't see something similar to that, then something might be going wrong, or maybe what is happening. Then I have to go and check from my code. So having done that, the next thing that we also look at is what's the sensitivity analysis. So for example, we have our transmission rate for this as to be 0.2 per day. But what about if I increase the transmission rate to 0.4, if I double it, or if I increase it to 0.8 per day, what happens? So then I can also begin to explore that, because intuitively I should expect that the more I increase the transmission rate, the more I should see that people will be coming into the I class. Okay, they will be coming to the I class. More people will be coming to that per day. I issue something that should inform me based on the model structure that we are using. And then lastly, the outcome that I'm having, are they really conforming to what I expected? Even as we are just discussing that if we increase the transmission rate, definitely cases have to increase, and even as cases increases, that decreases more the susceptible population. So this is something to be that this should be something that I should expect. But if I don't expect that, then I should go over and say, okay, what is happening? Is it that I missed something, or what is happening? Is there a different dynamics that I didn't consider? What is happening? Then that comes with that question. So what is the next step from this? Now the next step is, can we introduce an intervention into this? Now I know some of you are working on models that include interventions. So someone might ask, okay, if I want to include, maybe we've discussed how to write my equations, how to come in with my parameter values, how to come in with my initial conditions, how to do the running, how to check my whether everything is fine, doing the sanity check, how do I check the sensitivity of my parameters. I've done all these, but I still have one parameter that we have not talked about is an intervention. So, but I have an intervention in my model. So how do I go about that? And that is where we are going. So let's assume that we want to, so for this model that we are just talking about, we want to vaccinate people at time point 100. That's for example, and maybe we are running the time point from, maybe we are considering maybe 1,000 time points, or maybe almost 3 years. So if that is the case, if we are to introduce vaccination at the 100 time point, what should be happening? That is, or how do I introduce that vaccination at that 100 time points? Of which I'm going to consider different vaccine coverages. So I'm first going to consider where the coverage level is 0. That means coverage level 0 means there is no vaccination, in other words. So for example, if I say the coverage level is 0 and I'm still experiencing cases, then there should be, it means there's something wrong. And when there is a coverage level of 0.2, maybe 20% of the population is getting vaccinated. So what should happen? Then that means I should see lots of people maybe moving directly straight away from the S to the R without getting infected. Because given that the vaccine offers permanent immunity, so there's no way we are going to have a vaccine waning. So people will be coming back to the susceptible class. And for example, if we also consider, what about if the vaccination rate is 1? What happens? So that means at that time, everyone in the susceptible class just goes to the recovered compartment. And these are all things that you have been doing, and I know you have experience in that. So maybe what about maybe time point 100? There was 20% vaccination of this group. In time point 200, at that time there was maybe 0.5 vaccination coverage rate, because we had a lot of education and things like that. So then they are here. So let's see how that is done. How do we introduce vaccination to the model? Now, because we are dealing with, even as I mentioned, all the things that we are discussing, the key thing is all that we aim is understanding. If you understand it, there are so many ways to do it. There are so many ways to do this. And I know after this, some of you are going to come with different approach and wonderful ways of also doing the same thing, which is fine. So just continue to explore more. So what I'm trying to do here first is I want to define the time point. So I want to define the time point. I want to define that benchmark where I can then use that to try to track my timing. That's what I'm going to do. So what I say is, okay, I'm going to define the time step to be, and I explained to you that user means you are going to, that is a parameter that you are going to apply the value later. But if I put 1 here, it means that default, it can take that. Even if I don't supply it later, it can take 1. And I'm saying that my initial time step is 0, but I want to update it at every time step. So at every time step, what is going to happen is, let's assume that we are at the time step so 1. So at time step 1, that will be my 1. Sorry, this should be time. Sorry, but I've corrected that in the main code. Okay, so this should be time. Okay, so I'm going to update that time. So then if the first time is 0, then that means this will be 0 plus 1. But my time step is 1, so that will be 1. So that is the first time step. That's taking one. The value is 1. Then so now this becomes 1. That's changed. So then the time step 2 becomes 1 plus 1. Then that would be 2. Time step. So now this updates to become 2. Then time step 3 will become, already I have 2 here. So 2 plus 1. Then that becomes 3. So this also update become 3. Then time step 4 becomes 3. This is already, it updated to be 3, become 3. So 3 plus 1 becomes 4. So that is what I need this. I need to create this for me to get the vaccination to be implemented. So then in the same equation that we just talked about, so where I've highlighted red, that's where we are putting the vaccination. So I did not change the previous one, the main equations, I did not change them. They remain the same. But let's see, I just came with a condition, okay, a condition. And all that I'm saying is, if my time, that time that I just explained, is equal to 100, because don't forget, the question was, we want to implement the vaccination at that time point 100. So if man time is equal to, and that's how we write equal to in the OD model, yeah, is equal to 100, then vaccinate. So this is the vaccination rate, okay, either 0.2 or 0 or 1 or 1 or 0.4. So you are going to vaccinate those in the S class. Else 0. So that means that what I'm saying is, if any other time apart from time equal to 100, make the whole of these guys, the whole of this term 0. So that reverts to the main equation. Okay. If time is if the time point for my vaccination is reached, do the vaccination. Else, don't do anything. That's what that's what I mean. But then I also have to define where those who will be vaccinated will go. And that is why I brought the plus at the recovered. So then I'm taking people from here, but I have to balance that. I have to show where they are going, because we know that in the essence of vaccinations, you just want to want people to get immunized without skipping the I class. So then I have to take them directly to the R. So then I'm saying that if at the same time, so the same time that we are doing the vaccination, bring all those individuals to the recovered or to the immune compartment. So here we can think the recovery as a immune compartment. So then bring those individuals here so that they will skip the I. Okay. So then the same, I define the same initial states, the same user parameters, but the new parameter that I'm coming up with is the vaccination parameter. And that is what I set here. So once again, because I've brought user into bracket 0, this means that if I don't put anything, make it 0. But if I put something, so in the main, when I'm running, I can always change this there without necessarily coming here. So then that is what I was explaining. So then the same generator, so I define this to be my vaccination model. Okay. So this become my vaccination model. And then the same way, even as I did that with the previous one. So for example, I want to know if there is 100% coverage, then I just update that parameter, the vaccination parameter here. So if I put that in, then I get my generator. So this generator, now so I have a package. So my model parameters, my model equations, my vaccination rate, whatever, they are all here. So then I can call a run function in this to see my output. So here I was just trying to explain that the same way. So we want to run the same thing for 100, the same time period, okay, and the same approach that we use, even as we used it with the first. So we see that I just changed, or I just added few terms to change or to introduce my intervention. So it's not, sometimes you might think, these things are very difficult. You need to really learn coding for many years before you can do this, but that is not so. That is not so. It's all about you trying to understand what you're doing. If you understand what you're doing, then you just get these basics. Just get these at the tip of your hands. Then the rest is about, okay, how do I implement this? Okay, if I want to even do multiple vaccination, and even as I speak, someone has got an idea. For example, if I want to do vaccination at time point 100 and at time point 200 and at a time point 300, someone has got an idea. So you use the same if condition. If time point is this, do this. If it's not, do that. The same conditions, that's what you're going to use. So that brings us to this part of the section. Before we take our 10 minutes break, any quick question on all that I've discussed before we move to the next one after our 10 minutes break?
Yes, Mark. Shakira here.
Yeah.
How best that can be done?
So that's a very good question. So for example, you have an intervention like vaccinate. So we have one vaccination as one of your interventions, and maybe you have intervention like, for example, maybe lockdown as one another intervention. And so the question comes, are they all produced at the same time? You know better. So let's assume they are all introduced at the same time. So then questions also come. Okay, how do you see that to affect, or how do you see that to reduce transmission? Okay, then you think, okay, because the social distancing measure is something that affects the contact pattern, because the more we what do you call it? The more we are, for example, COVID, the more we are apart from each other, the lesser transmission. Okay, so then that means that there's something that's going to affect the overall transmission rate. Okay, the beta, because it's going to affect the contact pattern, which is embedded in the beta. So then you think about, okay, what do you want to do now? Maybe you might think that the first 6 months there was no intervention. So you say, sorry, let's use the first 100 days. So the first 100 days there was no intervention, which is fine. So then you maintain everything as it is. The beta is 0.2, you maintain it. But following the first 100 days, then we had vaccination. Okay. And then we also had maybe a lockdown at the same time. You could think about the same time. So if you had the lockdown at the same time, and we think that maybe the lockdown is able to reduce overall transmission rate by 20%. Okay. 20%. Let's assume that. So then what you are going to do in that case is you write the same thing here. You write the same thing here. But you come with another condition. You come with another condition that if for this part, then you come up with a condition that if time, so you write the same thing, if time is less than 100, then here, this is what you should do. Here, then you put the whole of this guy there. Because the first 100 days, there is no, there was no lockdown. So we maintain the same, this same thing here. Okay. Then you come with another condition. So else we are saying, so the lockdown, are we assuming that it goes on and on and on and on and does not stop? Let's assume that it goes on. So after the first 100 days, it goes on, it doesn't stop. So then if that is the case, they say, else, that means that, because here you mentioned that if time is less than 100, you should put this term there. But if else means what about if time is more than 100? Then if time is more than 100, because you are putting you are considering lockdown, then you take the whole of this term there here, and then multiplied by the you're saying that it is reduced by 0.2. Okay. So by 20%. So then you say that this becomes 1 minus that 0.2. Okay. That accounting for how lockdown was able to reduce the overall transmission. So that means instead of if we consider this to be the full transmission effect, then this will become 80% transmission effect. Okay, this will be 100% transmission effect, and then this part will be 80% transmission effect. So it depends on, even as I continue to say, it depends on what are the assumptions. What do we know? How that informs for you to know how to implement that here. Okay? I think that's I will not say this part is they are all important. All the parts are important. But the one depends on the other. So you cannot think about, okay, how do I put maybe intervention here without knowing, okay, what are the assumptions around that? Even as I was just trying to answer your question. I was saying, okay, let's assume that, because that will inform us to know when to put that in, and where to even put it, and when to put that parameter, or when to make that change. So that is the whole rationale about you trying to code your model. Okay. It's not difficult. And when we come from the break, you see that we're just going to go through the overall code in R. We are going to do that together. So I'll open my screen. You go through that, and after everything, you share with you the code and all the material so that you can also practice. The aim is following this. At least I think you can take it further. Try to implement that into the work that you already do, your research. Those of maybe you don't know which programming language or which coding method that you have to use, you can adopt this one, and then you take it further.
Okay.
Is that helpful, Sakila?
Yes, it is. Thank you. I'm going to keep trying out several things just in case I get stuck. I think I'll be reaching you via able. Thanks.
You are more than welcome. You're more than welcome. Okay, so let's take a break. Let's take a break. Abel, 10 minutes or 5 minutes? Abel, can you hear me?
Maybe might be engaged. But
Okay.
we could maybe go for 10 minutes
Call
and
me
then we
later.
get back.
That's fine. All right. See you at 7:15 UK time.
Thank you so much, Mark.
All right. No worries. Hi, everyone. Hi.
Hello, Mark.
Okay. Are you all
Hello.
set? Can I see from show of a thumb that are you all set? Can you show your thumb to me that you are set? Okay, I see Shakira is set. Okay, Alice. Okay, Brenda's also set. All right. Okay. So, in a nutshell, what are we saying? Okay, yeah. What are we saying in a nutshell? So this where we are. I don't think this is something new to you. And all the things here are what I was talking about. So this is the OD interface and it is in R. So the equations and the time step, the initial conditions and the parameters, they are all here. So just quickly going through them again. So we need to define the time. So we need to define the time that will help us to identify the benchmark or the point that we are going to introduce our vaccination. So then, even as I explained, we define the time step that at every point in time, it updates. So I mentioned about steps. So steps is, it can also serve the purpose of the time that I was talking about. It is a default timing in Odin. So when you even see the output, you see that one is already there. So it does the same work as what the new timing I am creating. I could have used steps instead of me seeing time as 100. I could have used step there. When we get there, you better get me. So talking about the main core equations, I have my susceptible, and this is how I define that, the movement in and out, and then I include vaccination. They say, so if time is 100, then do vaccination. Otherwise, don't do anything, or put 0 there, which literally means that don't do anything. So I do the same thing for the I compartment. I write the same equation even as we discussed there, and I do the same thing for the R compartment, but add the movement from the vaccination. I assume that okay, it is this R captures those who have recovered, and then those who are being immunized against the disease. So people just move straight from the susceptible to the immunity compartment. Then I have my total population. So I'm saying that at every time step, I update my total population to be the number of individuals in the susceptible, the infected, and then in the R or immune class. And I have initial condition for this total population. Because if I'm saying that this is the this make up the total population, that means that the initial condition also make up the total population. So I define the initial condition for each of the state variables, each of the compartments. So I define their corresponding initial conditions. Then I add a default value for the initial conditions, and then tell the code that I will supply this later by bringing the user function. And then I say that my vaccination rate is 0 by default. So that means that I can also say that since this is default, unless I change this model can be seen as something with no vaccination. Because if I say the vaccination coverage is 0, it's the same as saying there is no vaccination in the model. So that means the whole of this compartment, if it is 0, the whole of this will be 0, and the whole of this will be 0. But don't forget that I said if I put it into this, I can always change it when I am doing sensitivity around that. So I can always explore that. Now, so this is the Odin interface. Now let's see. Let me try to run this, and you see something. So if I try to run this directly, it will give me an error. So you see the error. Okay, it doesn't know. So this is not fine. We are coding in R, but this is not a normal R interface. So it doesn't understand the functions here don't understand the normal R that we know. Okay, that is why it's giving an error here. So when you finish with this, don't try to run this, but rather save. So save and then give it a name. So for example, I have saved mine as Indemu Odin source code. So I have saved it. I have saved it at where my directory is. So where I'll be doing the main running and where I will be changing the parameters, that's where I've set it to the same destination as this one. So it is saved at a place where I can easily retrieve that. Now let's see how we can merge this. We can put everything together and begin the simulation. So then I have saved this one. Then I come here. So this is Odin run. This is where all the running, everything takes. This is where everything takes place. So I have my working directory. So I've set a new working directory to be on my computer. You can also set the same thing on your computer, something, what works for you. You can set your working directory. And then even as I was talking about the SII generator. So in your code, so you need to first install Odin. I think I shared that with you, and then you library Odin. But me, because I've already installed that one, it automatically works for me. So that's all that you need. The only package that you need. So then I library it and then begin trying to ensure that I have this working directory. It's where the main source code is this one, and then this one is also there. So then I try to call this, I try to source the main code. So this is how I source the main code. So I just put the destination of the main code here. Okay. So you see where it is found, you see in modeling course, demo modeling course, documents, whatever. But the name of the file that I save is here. So you have to also do the same thing if you want when you are running. Other than that, you get error. So let me run, and you see. So all these phases, I'm just trying to call that function. So it is running. It's running. Yes. So now it is loaded. So now I have all the equations that I wrote here, everything, the parameters, whatever. They are all in this SIR generator. Everything is here. Okay. They are all here. They are here. So that's my generator for all the information. Everything is found within there. Then within that, I can then create something new. I can just say, okay, so if I had not already supplied this is an opportunity for me to do that. If I want, I can also just go straight away and run that. But let's see. Okay, I want to change things. So for my susceptible, I have 1,000 individuals as initial condition. For my I, infected, I have 1, and then my R, there is no one recovered at the first time point. That's what I assume. And then I have my beta transmission rate to be 0.2. I have my gamma to be 0.1. And then my vaccination rate, as usual, is 0, meaning that this is a baseline model. There is no intervention. There is no vaccination. So I don't expect to see any impact of vaccine in this model. So then for my time step, I want to see what is happening within the first 500 time point. And don't forget that I am running that for daily time step. And even as I mentioned, you can change, you can always, the T that you saw, sorry, let me go back. So this DT, you can always change it. If you want a smaller time steps, so this one means per day, you can try to break this down. So, for example, if you want to, for every day, you want to look at maybe 4 time points within the day, then you can break this down into 4. Okay, and so that will give you smaller window. But even as I explained, sometimes you not get data that is that will give you information for that smaller window. And it depends, of course, it depends on your work, the nature and the objective of your work. That will determine whether to use very small time steps or one just using a time step of a day will be okay. It depends on what you are working on. So then I have my time that runs from 1 to 500, and I say that I am now going to run my model. So this is the run function, okay, even as you saw earlier. But I just want to put everything into this data frame. So let me run that, run this, and then let me run my model. So you see, it is very quick. It's very fast. So you didn't even see that it took like just a second show, then everything finished. So then I can do the reviewing. I can look at what do I have in my as my output. So let's first look at some of the output. So this data frame that's called, so it stores my model output. So that is here. Let me see what I have. So I want to, and this means I want to look at the first 10 time points for the first row. So the first 10 time points, and then for all the columns, I want to, that's what this means. I want to view the first 10 time points for all the columns. Let's look at the output. So this is how Odin gives me the output. So you see, for the first 10 time points, so even as I explained to you that the steps is something that is already embedded in Odin, whether you bring, you don't need to bring that, it's already there. But this is a new timing that we created. That at time point 0, there's some time point 0, this should be 1. I mean, I should have started from 1, but it doesn't change anything. It's fine. Our time point, so let's assume this starts from 1. Or the initial time point. Yeah, that way, initial time point. This is the number of individuals in the population, the total number of individuals in the population. This is the number of individuals who are susceptible, number of individuals who are infected, number of individuals who are recovered. That's the first time point. That's what's happening. Then the second time point, we saw that number of individuals in the susceptible reduced. And then this one is now increasing because from the model structure, you saw that always people just move from the S to I without being replenished. So if you can track all the S, as time goes on, it is diminishing, decreasing. And then the I2 sometimes increasing. Okay, increasing. But maybe it's not yet to a time that it begins decreasing. And the R is also increasing. But let's check our total population. So at that first time point, we have 1,001. So you see that that is constant, which makes sense because no one is coming in and no one is going out from the whole system. So we expect that the total population remains the same. But if you are just looking at this way, so for example, if I'm running for maybe 30,000 or maybe 200 years or 300 years, can I have time to go through them one by one? No. So one of the best ways or more efficient way of you trying to visualize your output is to just do some plotting. So that's a very simple way of you seeing all that you have. So for example, I want to, based on this output, so I want to look at my total population as a sanity check. So does it remain the same over time, or is it something fluctuating? Now here it is higher and then here it is lower. So how I do that is, so they save this data frame that is here, my output. Then I say that, oh, for all rows, so for all the time step, I want everything, but choose only column 1. So you're going to only plot the steps against, for all rows I want it, but choose only my total population. That is, if you check, that is, so this is column 1, this is column 2, this is column 3. So that represents that. If I had put 4 here, it means I'm trying to work on the S. If I had put 5 there, and I mean that column, the whole of that column, and then the R is the C's column. So in your, if you do maybe in your work, if you when you finish, you see that sometimes it depends on how your model is. You might have several columns, but you just have to just track, okay, which column corresponds to my data, my compartment from the based on the output. So let's try to see the behavior of the total population. So I want to plot my total population. Okay, so it gives me an output. So this is my total population. And if you can see, so the total population is around here, 1,001, because when you check here, it's always around 1,001. If you see here, so that means it's something constant over time. It's constant for all the time that you consider our model. So it's constant for the whole 500 days. So that means I'm beginning to think that, yeah, things are really working. But that is not all. What about the main compartments? So what about the main compartments? Maybe let me try with the susceptible. So the susceptible is, it has column 1, 2, 3, 4. So that is the 4th column. Okay, then let me see. If I plot that, what do I get? How does it behave? Okay. Oh, so what it means is, okay, so it started with 1,100 and 1,000, sorry. Then began, okay, losing people. Okay, until it reaches equilibrium. Okay. But what about if maybe just looking at that one alone I might not see it well. So let me plot everything together. So then I come with lines for the remaining compartments. So then and the value is the same. So the 5th column is the R, sorry, is the I, and the 6th column is the R, even as we saw from the output. So we have the whole of our model. So we have the S being susceptible, that is shown by the blue color. So you saw that over time, the S is dropping until it reaches equilibrium. But those in the infected class, it also goes, it begins increasing, even as you saw. You saw from the output here. So it begins increasing, the I begins increasing until it gets to the time that it then begins decreasing, because the I can increase because it allows people coming in. And the same way, it can lose people. But if you check, my screen is something smaller. The legend is covering everywhere. But if you check the if you check the recovered, there is no way you see it decreasing. When you do it on your computers, you see it well. So there's no way the recovered is decreasing, but this one is, I just wanted to I'm not impressing. Okay. So okay, so I just want to show the dynamics. Oh, it's okay, that's fine. Let's maintain this one. I think, yeah. Okay, so okay, I just want you to show where the R goes. Yeah. Okay, so you see the R, it doesn't increase. Sorry, it doesn't drops. It always allows people coming in, but there's no drop in the R. And that confirms what we were seeing from the onset. That confirms the module structure because there's no way when people get to the R, there's any decrease there. So following the sanity check, so then we see, you can say that, okay, things are really working as expected. Then can we do some sanity? Such a way that maybe let's try.
Yeah.
We can look at,
Mark, can you hear me?
yes.
Yeah. Thank you so much, first of all. But I just want to request that you give chance to Rachel. Rachel
Okay.
had an inquiry just there on how to include, to add the legend, but also how to play with the parameters to ensure that she gets realistic simulations. Rachel, do you want to ask something, or we have answered your inquiry that you had in the journal club?
Well, yes, I would like to ask something. Mark, as I was simulating using the codes, when I checked my output, some of my compartments were negative to begin with, and I've seen when you checked your compartments, all of them were positive. So I don't know if that affected. And then over time, I tried to adjust the parameters because according to literature, there is an expectation of how the output should look like on the plots, and it wasn't working out. And then in the process, the number of individuals ended up being negatives. The time was in negatives. So it was really a mess, and I spent 3 days on the codes. So I need help from the start, actually. If I am to check my output, just checking the output in R and some of the compartments are negative, does that show that there's something wrong, and should they all be positives? And then now going back to the place where you need, also one of my challenges was it seemed like my values were the same, because I was looking at the 3 interventions, and then when I was running each line, I would get the same pattern. So when I wanted a combined output, I didn't get anything apart from 1 line instead of the 4 initially. Thank you.
That's a very good question. Thank you very much for bringing this up, Rachel. So the first question was, if you get, is there anything wrong if your output is showing some negative values? Very good question. So following all the discussions that we have had so far, we are dealing with population, and population, we are dealing with number of people. And there's no way we can talk about negative number of people. If you ask me as a mathematician, I would say, if you have a negative number, it is something good. But you will tell me, you as a clinician, and you know that we don't use negative values for people. Therefore, that is an indication that there's something wrong. If you see that the values in your compartment, there is a negative anywhere, this is the first indication that there might be something wrong in your equations. So maybe what you might be missing is, what you can do as a sanity check is you can go and look at the compartments. So the terms, maybe there was some movement of people, maybe there's a situation where always, instead of drawing people from a certain compartment, that term might be missing. Okay. So in this case, if we came with our I, where is our I? Let's do an example. So for example, instead of me, let me just say that the I is only updated by new cases. Okay. Let me just say that the I is only updated by new cases. So I just taking the I from here. So I is only updated by new case. That means it's like incidents. So only new cases is what is being updated. But actually it goes beyond that. So let's see what happens. I think that should give us something meaningful. And anytime that you do any change there, save. So if you don't save, it will retain the previous information. So you save and then come and run here again, the generator again. So for example, okay. So let's just look at the total population. What will happen to the total population? You know, even go further.
Yeah, Mark, just to give context, what happened is that Rachel has a very fantastic model, and she has complicated it. Actually, do you want to stop sharing such that she can just share her screen and you look at just the model structure alone? Because during lunchtime, in my opinion, I felt that she has begun on a high gear. She has like biting big, and she's struggling to chew it. You see what, Mark, you're dealing with. We are dealing with a kind of a simple model, the SIR. And from there, we can always improve it, update it, as long as we know that it is fitting. Maybe just share you stop sharing, and then she's just, you see what I'm meaning?
Okay.
Because
Okay,
she began in a high, with a bigger, with a very realistic situation, which is great, but for learning purposes and given the position she's at, for learning purposes, we could begin small and then we keep improving the model as we go on, or once we know it is working.
okay. Just a disclaimer, I actually did my model with the help of Mark, so he might know it. But let me share it right now.
Oh,
Yeah,
then he knows that's okay.
I would say maybe let's look at it again. Okay, let's look at it again so that we're able to finish this. We can look at that later. Yeah. And that's
we can look at the model later, right?
No, we can look at the code later, not the model.
Oh, okay.
Yeah, we can look at the code later. One thing that we have to also we can look at the code, the model later. Okay, let me put it that way. One thing that we need to be aware is sometimes these codes are not something that give a straightforward journey. Sorry, someone is making noise. Let me close my. Sorry. All right. Sometimes there might be something small missing, and it can take you several days. I think Alice, when we're working with Alice's code, still as of now we are just trying to wrap up. But one thing that I realized was there was something small missing, and it took us some time. So it's not something that we should. That is always a straightforward thing. You need to be patient. Sometimes the way you might expect to be finishing might not have it that way, but the fact that you are not getting doesn't mean all that you are doing is completely wrong. No, you might be missing just a term, and it can obstruct it.
Okay.
So we have to take that, bear that in mind.
All right.
Yes.
So,
okay, let me share my screen and we continue. Yes, Okay. So when you saw one thing, the small change that I made, if you can see what happened. So what I did was when I took off the I, so that means initially, what I'm saying, there is no initial condition, so there is no one infected. And if there is no one infected, then there is no way we can have any infection or recovery. That is why we are seeing this. So you see that small change. That's in my initial condition. So what I'm saying is in my initial condition, if I say that there is no one infected, then what I'm trying to say is, okay, so if there's no one infected, we know that the transmission rate, before we can, there should be transmission. This one has to multiply. So there should be a contact between this person and that, and the susceptible. So if this is 0, then that means that term always becomes 0. That is why here, for throughout the time, there is only a constant trend showing for the susceptible. So that is taking out the whole population. So that small change, you see what is happening here. Yes. So maybe you can run and get something like this. So you need to think away what is happening. Why I didn't include what is the missing thing. And this conforms to, this is consistent with what you know, because if there is no infection in the population, then therefore we cannot talk about cases. That's what this is showing. But so I just quickly I went back to redo that. So we can go back to what we were doing before Rachel's work. We were discussing Rachel's work. Okay. I want to bring this guy. Okay. Something. Okay. Top right, bottom right will have.
Mark, Mark, I wanted us with the fellows to discuss what they are seeing. We could just use what you're doing as a case study, such that they could see the potential implications. We are seeing, I'm just ask this, we are seeing a change in the diagram and a change in the positioning and so forth. What do fellows think is happening? Because if we can know what's happening in the background for us to see these changes on the diagram, we can replicate it later on when we are settled.
Yes, that's very important. Please, we are here. The whole of the course is let me say, it's about the pace that you want us to go. So it's not about me trying to share all that I know. It's about your pace. So yeah, we can reflect. How far, like so far, what do you see? How are you gaining some insight? Are you learning some new things? Or are you more confused or whatever? Let's talk. And if you are getting confused, what is making you confused?
Yeah, maybe just to ask again, just to add on Mark, I would be keen to hear from Brenda Yakam. We are seeing a change in the diagram. What do we think is causing this change? Because if we know what's causing the change in the diagram, we would be careful when we do such a change in the future. Brenda, do you want to give any your thoughts?
Okay, thank you very much, Abel. So from the diagram, first of all, you know, the model that we are trying to build is the SIR, which is susceptible, infected, and then recover. And just like what Mark already explained, so since we are moving from the susceptible to those that are infected to those that are recovered, so we see that the number of individuals that fall into the susceptible is actually dropping, as that susceptible level is more like minus from the equation that we previously had, or that was described in the beginning of the course. So we actually see that the diagram that we're actually having reflects our model, and it shows that as time is actually as time is progressing, the number of individuals that are susceptible are decreasing, and then those that are infected are also decreasing as time is progressing. That's over time, and also the number of people that recovered with time from the COVID-19 is also increasing. So that's basically what I can say.
Yeah, thank you so much. Maybe Shakira, before you come in, thank you so much, Brenda. Let's give another person another chance. What we are seeing a change in the diagram. What is happening in the background that is leading to this change in the diagram? Brenda Nakazi, were you able to make a comment on that? I was keen. I would see the diagram changing, but I want somebody to help me to understand what was happening in the background to make that diagram keep changing. Yeah, now it has changed again. Yeah. Brenda Nakazi, would you want to make a comment?
No,
No,
I will pass.
another Brenda.
All right. Okay, thank you.
Nakazi, were you able to make a comment?
Yes, I really like the insights that Brenda shared, especially when she mentioned this key, which really tapped me. That
maybe Marka, before you come, just one more comment. Shakira, do you want to make you had raised your hand? Shakira, we are seeing changes in the output. What do you think is happening?
Yes, I really want to make something here. So one should be able to appreciate that the rate at which the infected people are changing is a bit slower. But when we look at the susceptible and the recovered, there's sort of like an exponential increase or decrease.
No,
Decrease for the susceptible and increase.
Shakira, you're going so deep about it. I just wanted the fellows to understand. They don't explain what we are seeing. Maybe Alice has got what I was looking for. Alice, try to help me understand why was the diagram changing from time to time. Mark, can you try to show how it was changing, the outputs?
Okay.
The outputs.
Okay. To me, what I can only say or what I observed was from our equations, we had compartments from our model. So like when we started with the first model of first compartment of only susceptible, we were able to see only one line on the graph. So as we kept on introducing other compartments, the diagram also kept on changing. That's one thing that I observed. And then also as like the first one, Mark, the previous one.
Yeah, thank you.
Where we had one line.
Yeah, Alice,
yes.
Just because of time, thank you so much. And
Okay.
You've raised a very important point, which I want fellows to have at the back of our mind, that once we are adding on a compartment, we are likely to see a change in the output. Once we make a change on the equation, either we are introducing a plus, either we are introducing a minus, or we are eliminating the variable, we are likely to see a change in the output. If we make changes on the parameter estimates in the equation that we are fitting, we are likely to see a variation in the output of the diagram. Yeah, Mark, take it on.
Thank you very much, Abel, for that insights. And I am not going to talk more. So what Abel was trying to explain, I'm just going to show some figures on that. So now, and all that he said, like, that's the point, that things that don't just change. Things don't just change. It depends on, so what you put in will definitely, in one way or the other, depending on how it is related to the model, will have an impact on the model. So for example, let's try to play around our parameter. So let's assume that, for example, let's only consider the transmission rate. So here, the transmission rate is 0.2. So the rate at which people who are susceptible become infected, that is 0.2. Let's assume. So if I want to double that, can someone guess what is going to happen? So I want to make it 0.5 more. I want to double the transmission rate. So what do you expect to happen? Can someone share something quick so that we just run the code to see what happens? If the transmission rate, yes, Shakira.
There's going to be an increase in those who are infected, and then at slower, a much more decrease in those who are susceptible because of the increase in the infectious rate. Okay.
Let's see whether that conforms to what you're hypothesizing. So let's see the peak for the transmission rate. Now it is less than 200. That is the red one. Let's take note of that. And the susceptible to I don't think it goes below 200. So based on Shakira's hypothesis, she's saying that you're going to see an increase in the red one, the transmission, those in the infected compartment. You're also going to see a decrease in the susceptible population. So let's see whether that happens. But that's what she's suggesting. Now something from 200, now we see that it's moved to at the same time point. So now we are experiencing more than even 400 cases. So we see that there's that interaction and there is that impact. And that perfectly explains what Abel was saying, that wherever it's not every parameter let me say, it's not every parameter that whenever you change something, it will automatically change everything. There might be some, it depends on where they are, their impact will vary. So there are this parameter, when you change it, everything else will change. But there are some when you change, maybe it will only affect some specific part. So don't also assume that whenever you change the parameter, you have to see a total change everywhere. No, it depends on the role that it is doing. And the transmission rate is very key in this. So definitely when we change that, there's going to be that massive impact on all the compartments. Now, in the same analogy, so here we increase the transmission rate, but see something. The moment at the same, so like there wasn't any, fine, we have a sharp increase in those who are in the infected class, but they couldn't stay long. They couldn't stay long. You see, like it didn't take much time for them to decline. And we see that from the recovery rate. So the recovery rate is fast. Okay, so whenever it gets to that time, it drops. But let's see, if you consider a lower recovery rate, what are we guessing? So for example, under a situation where we have doubled the transmission rate and the recovery rate is something, we reduce the recovery rate. So what happens to those in the especially those in the infected class? So maybe instead of 1, let me make it 0.01. Recovery rate per day is 0.01, something very small. And let's see what happens in the whole system. So you saw that initially the drop was here, like it was just here. Let me see that. Why is this one? Okay, that's fine. So initially the drop was just along this line. It was here along this line. But because now, and then even the peak was not up to here. Okay. Okay, what do you see? Sorry. What do you see? Has there been any change? What do you see? And
Yes.
what can you comment on this?
Can I go?
Yes.
Yes, so since we reduce the recovery rate, it means that there is going to be a slow movement of individuals from the infectious status to the recovery status. But remember, we did not change the movement of the infectious rate, right? So we shall be having so many people coming in from the susceptible compartment to the infectious compartment. However, we have a slow output from the infectious compartment to the recovery compartment. And that's why we're seeing the number of individuals in the infectious compartment almost getting equated to, to those initially for the susceptible, because there's a slow movement from that compartment to the recovery. Yes.
Very insightful. Before I end this session, so one key thing is, you see, always, irrespective of the change that we effect, irrespective of whatever we are, so you saw we've made about 3 or 4 changes in the parameter, but you see this guy, the recovery individual compartment always increasing. The worst case was maybe to increase to some time and then just take an equilibrium. There was no way you saw it declining. I don't know whether you've identified that. If you have identified that, what do you think might be causing that? Why is it that the recovery compartment, it always increase? The worst case scenario is when it takes equilibrium. Just maintain it in state to be constant. Why is it that it is not decreasing? Meanwhile, we can experience a decreasing in the susceptible, can also experience a decreasing in the infected. Why is it that the recovery is always decreasing? And I want you to
that.
Can anyone different? Okay,
okay. Let me give Alice the opportunity. Over to you, Alice.
Yes.
Okay, thanks so much, Mark. Maybe just my thinking is that why we have always recovery increasing. Okay, first of all, maybe it will depend also on the model that you're dealing with and the disease itself. Because like the recovery here, we are dealing with only 3 compartments, which is the susceptible, infected, and recovered. And we do not have the death compartment. In cases whereby we do not have the death compartment like the way we are having this, it means that to me, my explanation would be that after seeing this graph, I would think people are getting infected and the rate at which they're recovering is a little slow, and that makes more of the persons to get ill. But however, that almost everybody is becoming ill of this infection, the infection is not so dangerous that it kills people. So at the end of the day, all the sick people at one point have to recover, though the recovery is slow. But then in cases where we do have the death compartment, and this could be an infectious disease any other disease whereby it involves death, and we may be having that death compartment. That means that in me, I'm just thinking in my mind that the slower the rate of recovery, then that means that we may be having many people dying and many people getting infected, and most of them will be dying, and our recovery rate will be very, very low. So that is what I would think of after looking at this graph.
Thank you very much for that insight. Shakira wants to add something to that.
Yes, just going to add something. Maybe from the question.
Yes. Yeah, for us to give chance to other people, just to ensure that people are not dozing. We maybe have another person than the vocal candidates. There are some who may be vocal and may suppress others.
Yeah. Okay. So yeah, I leave that to you. Yeah, you can just.
Okay. Let me just give chance to George Napulu I know he missed some of the sessions, but I just want to be sure if he's following, and he's trying to work on the model, and he was struggling at this part. But he wanted to use his differential equations background to explain. George, do you want to make a comment on Marcus' question?
Thanks so much, Abel. Thanks so much, Abel. I'm following closely.
So do you have any idea about the question? That's why? So why is it that always those in the recovery compartment, they are always increasing? The worst case scenario is when they will take equilibrium position. There's no way you see that will be also declining. Why?
I don't have an idea yet.
Oh, no problem, no problem. Yeah, we are just trying to put things up. No problem if you don't have any idea. That's fine. Yeah, that's fine. Yeah. Okay. Any other person who has not spoken today? Does anyone have any idea as to why they recovered? They are always increasing. So the answer is here. Let me show you where the answer is. Now let's look at the previous session that we had, and even I just also explain it. Let's look at the equations, the terms that make up the recovered compartment. You see that the recovered, do you see any negative sign anywhere? There's no one moving out at any particular time. Always it is receiving people. Always, so it's like people will just be compounding. People will be compounding. So either vaccination, they will come, but here we don't even talk about vaccination. When you recover, you come. When you recover, you come. So it is always receiving people. So there is no way we are going to experience a situation where it is now going to reduce or lose people. That is why it is always increasing. But for the infected, if you see, we can see that at a certain point in time, so though people will be coming in from the susceptible here, that's the meaning of this term. These are people who are coming in from the susceptible into the I infected class, but they will be recovering. That's the negative. They will be recovering. So maybe at the initial, so here, even for the first, at the starting point, these two were interplay. So those who are coming in and those who are going out were still interplay. They were still, those two dynamics were going on. But we're still seeing the increment because those who are coming in supersede those who are going out. Okay, those who are coming in were more than those who are going out. So still, balancing everything, you still see that there will still be an increment at the end of the day. But when it gets to this situation, this is where those who are going out are more than those who are coming in. When it is declining, the infected. Those who are going out supersede those who are coming in. So fine, people are still coming in. Though people are still coming into the eye, but those who are going out is more than those who are coming in. That is why we are seeing it's increasing to some point and then decreasing until everything, like it gets to a very small value. But for the S, if you see the S, there is no way people are coming in. That is why we don't see any increment in the S. Okay, there is no way you see an increment because if you check here, this is the original S, and then aside that, these guys, they are going out. They are always moving out. So there is no way we should expect maybe at time point 100 you see a slight increment or whatever. There is no way that's going to happen. As long as we continue to keep this equation, this will be the dynamics, and this is the sanity check that we are talking about. So you have to explore your model in all this to ensure that, okay, what even as Shakira mentioned and Brenda mentioned, yeah. So what I have inputted here as my equations, am I seeing the same thing in the output? That's the meaning of sanity check. Am I seeing the same thing? And then sensitivity comes when you see, okay, what if I increase this parameter by this? What if I decrease this parameter by this? Does it have any change? Does it have is there any difference? So I think, Abel, we can end here today so that tomorrow you continue from here. I think for now, I see that we are going to benefit more if we spend some time thinking about looking at tomorrow. You spend some time looking at lots of scenarios and then trying to explain and become very acquainted with that and link that to our model equations. And I think that will help us get more insights into doing our work. Abel, what do you think?
Yeah, that's a great one. I'm in agreement.
Okay.
And the fellows,
Okay,
should know that we are closing tomorrow.
Yes. Alice, you've raised your hand. Any questions?
Yes, thank you so much, Mark, for today, and thank you so much, Abel. Mine is a request that maybe if you could share with the team this script, and we use it as an example to do more learning as we wait for tomorrow's session.
Definitely, we are going to share it. You're going to make it ready. It left after
And the recording, please.
Okay. Okay.
Thank you.
You're welcome. Abel, your final remarks, and then you close for us.
No,
I'm
grateful to the fellows who have created time to come and learn, and we learn together. I'm learning a lot from the sessions, and I'm eager to see how far we shall go tomorrow. Thank you so much, Mark, for creating time to come and take us through, and we are very grateful.
It is a privilege, my brother. I'm also very grateful that you've all been able to come and we are all learning together. We are there for each other. So yeah, we are together. Let me put it that way. So I'm a brother to you all, and you're also family members to me. So I see this as something that we are doing at home. So very happy to collaborate with each and every one of you, even as we move along. Okay. Then, in the absence of any further question or clarification, we're going to pause here and we continue tomorrow. Have a wonderful evening, and I think good night. Yeah, it's night in Uganda. So good night and see you tomorrow. Bye-bye.